Here's a few more L'Hopital's rule examples, focusing on a few complexities you can have. And I want them both making them meaningful. They're both interesting questions. One is we have this very, very important approximation that sine of a small angle is approximately that angle. Sine of x is approximately x for small x. And I want to talk about, well, how good an approximation is that? And looking at some other limits and using L'Hopital's is a really good way to do that. So another way to say that is that the limit is a very famous limit. It's basic to why we know like the derivative of sine x and cosine x at all, is that the limit as x goes to 0, sine x over x equals 1. Okay, so let's investigate that. So that says the ratio of those two things is equal to 1, but that doesn't mean it's exact, and it's clearly not exact. Sine of x is a wiggly function. It's not a straight line function. So let's take the limit as x goes to 0. Let's take sine x and subtract off that approximation. So that's the difference between the real thing and our approximation. And then compare it to something that's going to 0 really quickly. And that's x squared. If we did just x on the bottom, all we would be doing is take the limit of sine x over x minus 1, and we know we'd get 0. And that's because we're comparing sine x minus x to something that's small but not super tiny. But let's instead compare the difference between sine x and x to something that's quite tiny, x squared. Let's see what happens. That's not guaranteed to be 0. Okay, and this is a great case for L'Hopital. The top is going to 0, the bottom is going to 0, everything's continuous, all derivatives continuous, everything like that. And so it's the same thing as the limit of the derivative of the top over the derivative of the bottom. Okay, now this is a great place where L'Hopital's rule gets used more than once. This is still, the top is still going to 0 because cosine of 0 is equal to 1, and the bottom's still going to 0. And everything's still nice and continuous, but this is exactly where it's great to use L'Hopital's rule more than once. And so we can take the derivative of the top again, and the derivative of the bottom just turns into 2. Okay, now the bottom is not going to 0. That's really where you want to end up at. The denominator is not going to 0. But sine of 0 is still 0. So in fact, the limit is 0. That's actually really telling. It says that take the difference between what could have been a very crude approximation to sine x and sine x itself, that's the error, divide by something very small, and you still get 0 in the limit. That says this is actually a surprisingly good approximation. That didn't have to happen. So let's keep going. Well, wait, maybe even if we compare it with x cubed, we might get 0. X cubed when x is small is really tiny. Well, so we just change that to a cube. Okay, very similar here. First few steps are very similar. We should still use L'Hopital's because it's still, the top is going to 0, and the bottom is still going to 0. Okay, so we use L'Hopital's runs. Oh, one thing I want to mention. Here I don't think it's super tempting, but it's very easy. When you use L'Hopital's rule more than once, it's very easy to use it too many times. The reason we could use L'Hopital's rule again here, and why that was appropriate, is because it's still a 0 over 0 indeterminate form. And this is not. Don't use L'Hopital's rule on this. If you use L'Hopital's rule on this, you're going to get nonsense, because it's not a 0 over 0. So if you're in a situation where you think you're using L'Hopital's rule more than once, make sure that every time you use it, it really does apply. If it doesn't apply, you probably didn't need it anyway, and so you're probably overcomplicating things, but you can definitely just get a flat-out wrong answer. Okay, so now this is exactly a place where we're going to apply it more than once, because the top is going to 0. The bottom is still going to 0, so now we take a derivative again. Okay, and, okay, now we're going to use it a third time, because that's still the limit of f over g. Limit of f of x is 0, limit of g of x is equal to 0. Everything's continuous and nice. So that turns into cosine. And finally, we've eroded that x cubed enough that it's going to a constant. Whenever you have something like this, limit of some interesting function over like just a polynomial, or just like a monomial here, just a power of x, L'Hopital's rule multiple times should be your instinct, because we know the bottom's going to become eventually a constant, and eventually that's going to work. As long as we just know how to take the top derivatives and it doesn't get ridiculously weird, you're going to be able to do this basically. Okay, so now that turns out to be minus 1/6. Interesting. Okay, so a way to say this is that we found something very interesting about sine. Sin x is not only approximately equal to x, if you just solve this for sine x, it turns out sine x is approximately x minus x cubed over 6. That's a very interesting answer. It tells us a much more sophisticated approximation than just sine x is approximately equal to x. So there's really something very, very powerful that comes out of that. And that's actually the start of a story that we'll come back to toward the end of the class. Okay, so here's another one. I wanted to do one where we have to do logs, where you're doing limits of powers and stuff like that. So probably you've heard that 0 to the 0 power is not really officially defined. It's a bit weird, and it's not a good idea usually to define it, although in some situations we almost do define it. But one of the classic L'Hopital's rule with powers examples is that the limit as x goes to 0 of x to the x actually does exist, and it's equal to 1. And so that what that says is if you put a small number as the base and the identical small number for the exponent, you get something really close to 1. So for example, 0.001 to the 0.001 power, if I have the calculator or the computer just evaluate that, I get something pretty close to 1. And if I do another 0, notice to get an understanding, this isn't how I'm going to prove something, but to get an understanding about limits, we can always go back to that tabular approach. Okay, looks pretty good. When this is getting closer to 0, that's getting closer to 1. Okay, so that would kind of, it's really getting close to what it would be if I just went ahead and cut to the chase on the numerator. The exponent, and I got 1. So I would say it sort of seems like the exponent matters more, because if you actually say, if you do 0, if you replace the base with 0 and take it to a really small number, you get quite a different result. Of course, you get 0. So somehow it seems like in this expression, in the 0 to the 0, it's kind of trying to pay more attention to the exponent. That seems to be what this result is saying. Well, but let's try something where they're not identical quantities. We take a fairly small quantity x, and then I'm going to take it to the 4th root of x. So for example, that might be like 0.001. That's 1 over 10,000. Let me clean this up. Let me just remind ourselves that 1 over 10,000, I'll put it in math mode, is 0.001. Okay. And I'm not going to raise it to something so darn small, something so close to exponent 0, which would seemingly give me something that wants to be 1. I'm going to raise it to the 0.1. So here I'm taking something that's very close to 0, and remember, if the base is exactly 0, I'm going to get 0. And then I'm raising it to a power that's not nearly as close to 0. So even though when I raise something to the exact 0 power, I'm going to get 1, I'm not so sure about this kind of pattern. And this is an example of the kind of thing you'd get here, where we take x, 1 over 10,000, for example, and raise it to the measly 1 over 10. Or I could have 1 over 100 million, maybe, and raise it to the 1/100th power. Let's see what happens. This is exactly the kind of thing L'Hopital's rule is good for. Well, first of all, let's see. What is this? I don't have a good guess based on that one example. I don't know if that's really kind of going towards 0 or going towards 1. It's really hard to tell in this example. And that's the limit of, the limitation of doing things in a tabular method in some cases. You might be misled. So here's the thing about this guy, right? We're going to call this L. This is a classic example of doing L'Hopital's rule with a log. We're going to take the ln of L. That's the ln of this limit, the natural log. I know people in my videos sometimes have complained, don't say ln, it's natural log, or just log. But I like to say ln to make clear it's not the log base 10. Okay, so really crucial thing is that the natural log is a continuous function. And so the log of a limit is equal to the limit of the log. That's really a pretty important, subtle thing that we're doing there. And now the log is taking, is seeing that exponent. That comes down in front. I don't really need parentheses. Okay. Okay. So wait, now how's L'Hopital's rule supposed to apply here? Remember that whenever you have a product, let's see, why is this indeterminate? It's indeterminate because the 4th root of x is going to 0, and ln x is going to minus infinity. So it's a 0 times infinity type indeterminate form, and I really need to write it as an infinity over infinity or a 0 over 0 type expression. And so one of these guys has to be written as a reciprocal of its reciprocal. And probably doing that with 1 over ln is probably not such a great idea. So I'm going to write this as ln x over. So that was x to the 1/4, so I'm going to write it as x to the minus 1/4. Kind of a weird thing to do. I'm writing x to the 4th root of x, in other words, x to the 1/4, as 1 over a negative power. That's sort of the opposite of traditional simplification. But here's why that's useful. Okay, when x goes to 0, x to a negative power goes to infinity. ln x goes to, well, it turns out minus infinity. Oh, and I want all these limits to be 0 plus, sorry. It doesn't make sense to put in negative numbers into this ln. So to be a little more careful, I'm going to put in 0 plus. Okay, and then now I'm finally in a L'Hopital situation where I've got exactly the kind of quotient indeterminate form that it applies to. Oh, and I've already copied it. Now I can take the derivative. I get 1 over x on the top, and I get minus 1/4. That minus sign isn't coming out very well, is it? Sorry, there's a minus sign there, but I feel like it's being very small, very thin. Okay, increase the magnification a little bit. Okay, and then x to the minus 5/4. Okay, has that helped? You bet, because it's all algebra now, and I can just simplify that. Now I can actually bring the x to the 5/4 back up top as a positive power. I'm going to take this out as a minus 4. So dividing something by minus 1/4 is just minus 4. And actually, let's just rewrite that with the x on the bottom here. Oh my goodness, that's really not so bad. That is just minus 4 limit, oh, I got a lot of extra stuff here, of x to the 1/4. I'll just redo it from scratch. And that is equal to 0. Okay, now, does that mean the original limit we wanted was 0? No. It means that, let's scroll up just a sec, the log, we had this trick where we took the log of something first, kind of like logarithmic differentiation. So we're saying that ln of L, let's do that, equals 0, so L equals 1. So it turns out the limit actually still is going to 1. Even when you take expressions like this, where you're really trying to bias it towards giving the 0 to anything answer, which would be 0, it actually is biased still towards the exponent. And this guy is actually equal to 1. Cool, that'll be it.